Hi, I'm Brian Pruitt tutoring high school physics. Today's topic, centripetal acceleration and force. If you've got an object moving in a circle, it's constantly going to be changing direction. If it's changing direction, that means it's changing velocity, because velocity takes direction into account. And if it's changing velocity, that means it must have an acceleration. We call that acceleration centripetal acceleration, because it's spinning in a circle. So here's the formula for it. We define it as the tangential velocity squared divided by the radius of the circular path. So what do I mean by that? Well, here we have an object traveling in a circle. If we take a snapshot of it at any moment in time, we'll find that its velocity points tangential to the circle. And so this particular object, weight, has a mass of 5 kilograms, the radius of its circular path is 5 meters, and it has a tangential velocity of 5 meters per second. So we can find the centripetal acceleration for this. We just refer to the formula. We have our tangential velocity, 5 meters per second, squared, and then we're dividing that by the radius of a circular path. 5 squared is 25, divided by 5 is just 5 again, and so we're left with 5 meters per second squared. Okay, what about centripetal force? Because where there's acceleration, there's force. Well, recall that force equals mass times acceleration. In this case, we're going to find centripetal force, so F sub c, and acceleration is going to be centripetal as well, so A sub c, just like up here. We could just use this equation to find out what our centripetal force is. So we have a mass of 5 kilograms, and we already calculated centripetal acceleration. And so we get 5 kilograms times 5 meters per second squared, or 25 newtons. Alternatively, we can substitute in this v squared over r to find that our centripetal force is mv squared over r. And that would have been faster if we'd only wanted to know force, instead of first calculating out our centripetal acceleration. One final note about centripetal force. If you have an object that is traveling around in a circle, so it has centripetal force, that force will always point towards the center of the circle. Okay, with that in mind, let's do an actual problem. You may have noticed that if you throw a ball into a cup, it'll spin around at a specific height before dropping to the bottom. How does it do that? Well, it turns out that that depends completely on its centripetal force. So, for this ball spinning in a cup, the ball weighs half a kilogram, and there's a frictional coefficient of 0.7 between the ball and the cup, and the radius of the cup is 0.03 meters. What is the minimum speed necessary for the ball to be spinning at for it to stay at this particular height? Well, first we'll have to draw a free body diagram. We already know that centripetal force points towards the center. But wait a minute. Where's that coming from? Recall that you may have tossed a ball and giving it its velocity, but something must be exerting that centripetal force on the ball pointing towards the center. Turns out it's the cup, and according to Newton's third law, for every action there's an equal and opposite reaction. Not only is the cup exerting a force on the ball, but the ball is exerting a force on the cup in the equal and opposite direction. Notice that this force is completely perpendicular to the wall of the cup. So this force is in fact our normal force. So that means what's going to happen is that although the force of gravity is going to pull the ball down, the force of friction is going to oppose that motion and keep it up. So here's what's going to happen. We're going to have our force of friction must be equivalent to the force of gravity in order for the ball to stay up. So this is just kind of our starting state. Recall that the force of friction is equivalent to the normal force times a frictional coefficient. So we're just going to substitute that in, equals mg. And here we found out that the frictional coefficient is 0.7, but also that the normal force is the equal and opposite reaction to the centripetal force. So if we find the centripetal force, we found the normal force. So we can just substitute that in. Our centripetal force is mv squared over r. We're going to multiply that by mu equals mg. Okay, so there's some simplification that can happen. We can get rid of m from both sides of the equation. You know, it's v squared over r times u is equivalent to the acceleration due to gravity. Okay, so let's start throwing in some numbers. We don't know v squared. We know that our radius is 0.03 meters, and we know that we have 0.7 as our frictional coefficient equals 10 meters per second squared. Okay, so we can punch this all into our calculator. We divide both sides by 0.7, we multiply both sides by 0.03, and then finally take the square root. And after all of that, you'll actually come up with a velocity of 7.14 meters per second. So our ball has to have a tangential velocity of 7.14 meters per second to stay up in this cup. Alright, to recap. Centripetal acceleration is defined as the tangential velocity squared divided by the radius of the circular path. So for something spinning, if you stop it at any moment during its spin, it'll have a velocity that's pointing tangential to its circular path. You can also find the centripetal force by multiplying the centripetal acceleration by the mass of the object spinning. Or if you want to get straight to the centripetal force, you can define that as mass times velocity squared divided by r, where r is the radius of the circular path. Alright, that's all for now. Again, I'm Brian Prier. See you next time.